Great, thank you very much, and thank you to the organisers for inviting me to speak here. It's my first time at Simon's, and it's been great so far. So I should also apologise to people who were in Bonn a few weeks ago, who will have heard me give exactly the same talk, and really apologise to those poor souls who will also be in Oxford in a few weeks' time, who will hear the same thing for the third time. But I hope that for everybody else, you'll get something from this. So the talk is about two things which different groups of people in the audience know something about, but maybe somewhat disjoint groups of people. So the Riemann Zeta function, so there are plenty of people here who know something about that, and also multiplicative chaos. Okay, so there are plenty of people here who know more than me about that. And I want to try and explain, not really the Riemann Zeta function, but multiplicative chaos, so that everybody has some kind of understanding of it. And I want to explain what the connection is between these things. So the plan is to explain, not exactly, but kind of roughly, so you get some idea what multiplicative chaos is about. And then there's a whole class of multiplicative chaos measures, and there's one which will be particularly important for me today, which is the critical chaos. And I want to explain what that is, what that means. And there's a conjecture of Saksman, who is here somewhere, and also Christian Webb, which says that powers of the absolute value of the Riemann Zeta function on the critical line should somehow produce these chaos measures. I want to explain, again, roughly what that conjecture says. And then I'll talk about some work in preparation, so hopefully by the end of the year, maybe this might be out, of myself and Saksman and Webb, which proves the critical case, also the first known case of their conjecture. Okay, so I encourage you to interrupt if you have questions at any point. I want to try and make everything clear. And if you're not so keen on the probabilistic stuff, if you find yourself kind of tiring in the first 3 points of a talk, in the fourth part, when I discuss the proof of our result, there are some basically purely number theoretic ideas there, which I think are quite nice. So if you've given up by that point, you can wake up again, hopefully, for the end of the talk. Okay, so this workshop is about universal statistics in number theory. What does that mean? Okay, so there are some probability distributions which occur all over the place in mathematics. The Gaussian, the normal, would probably be the best example. Okay, so the Gaussian we've known about for at least 200 years. I guess it occurs all over the place, and it occurs in number theory, even in situations where you might not expect it to. So we heard about the Erdős-Katz theorem in Demetrius's talk yesterday. The number of prime factors of a random integer has a roughly Gaussian distribution. I'll talk later today about the Selberg central limit theorem that says that if you look at a single random point on the critical line, the log of the zeta function has a roughly Gaussian distribution. Okay, and we know that there are other more complicated probabilistic objects which also have connections with number theory. So the eigenvalue statistics of random matrices we've known for maybe 50 years have some kind of connection with L functions. And multiplicative chaos is an even more recent class of things, so studied maybe first by Kahan in the 80s, which I will try and explain to you roughly what they are. They're a bit more complicated, let's say, than just the Gaussian distribution. I hope I can give you some idea. And it turns out that these also have strong connections with number theory. I want to explain that. Okay, so what's the basic idea here? So we take some collection of random variables, x of h, indexed by some set, and you can think of the set that's indexing as just, let's say, an interval on the real line. And we're going to try and form a random measure, a random weighting from these random variables x of h. And the way we're going to do it is we're going to integrate test functions, nice test functions, against exponentials of these x of h's. Okay, so we want to try to understand objects like this. So we're integrating over our set curly h, just thinking interval, some nice test function g of h, so think a continuous function or a step function or something like that, against e to the gamma x of h. And for any given test function g, we can evaluate this integral, hopefully. And because the x of h's are random, for any given test function g, this will be a random number, a random variable. Okay, and so we want to understand the distribution of this random variable for different test functions g. And in the construction, there's this parameter gamma here in the exponent, which is usually taken to be a positive real, let's say, and that plays a role in the chaos measures, which I'll come back to later. Okay, so I hope that the kind of basic idea is not too difficult. So we have our starting random variables x of h. We form a measure by weighting the Lebesgue measure, dh, by the exponentials of these x of h's, and we see what we get. Okay, now, as I've set things up there, it's far too general to hope to be able to have any kind of nice theory. So we need to make some restrictions. Okay, and the usual restrictions are, first of all, that the x of h's should be Gaussian, or at least roughly Gaussian. And that's because if we can't do the Gaussian case, we probably can't do anything else. Okay, so I hope that's fairly natural. And then also that the now Gaussian random variables x of h should have mean 0 or close to 0, and variance. So if the mean is 0, the variance is just the same as the mean square. You want the variance to be the same or very close to the same all points h. Okay, and why is that? Well, if you go back to the definition here. So what I'm doing in this integral is I'm weighting the point h by e to the gamma x of h. Okay, and that's a random number. But we can think about the kind of usual weight that gets assigned to the point h if we take the expectation. Okay, so this is the expected mass that I'm giving to the point h. And if x of h is Gaussian, this is just the moment generating function of the Gaussian, so we have an exact formula for what this is. Okay, this is what it is in the Gaussian case. And you can see that if the variance is big, more mass is going to those points, usually. Okay, if expectation of x of h squared gets bigger, this thing is getting larger. So if there were some points h in the integral where the variance were much bigger than at the other points, those points usually would be dominating the integral, and it would make more sense just to separate those out and look at them on their own. Okay, so if you want all the points in the integral to have a chance of doing something, you should assume that the variances are pretty comparable at all the points. Okay, so I think that the first two conditions are fairly natural. Now, what's much less clear is the third condition here. So fortunately, something vaguely like this was mentioned in the previous talk, so I can defer to that a little bit. So what we want is that the x of h's, they know something about each other. Okay, so here there's this spatial variable h, and we want the spatial variable to be doing something. So we want x of h and x of h prime, if h and h prime are close, to be kind of close to one another as random variables. And more specifically, what we want is that when h and h prime are close, x of h and x of h prime are very highly correlated, okay, very dependent. And then as h and h prime get further away, the correlation goes down, so they get closer to being independent random variables. And it turns out that the way that the correlation should decay, to get a nice theory here, is logarithmically in the distance. Okay, so this is the same thing that was being discussed before the break. So I won't say much about that. I'll say a tiny bit more about that later. But it turns out that this is the condition that you want to have to get a nice kind of structure here. Yeah, so just to emphasize in particular, so the x of h will not be independent. Okay, we don't want that. We want that when h and h prime are close, they're very dependent, very highly correlated. And then when h and h prime get further away, they become closer and closer to being independent, and in this particular way, in this log correlated way. Okay, so what does this have to do with number theory? Well, it turns out, maybe surprisingly, it has a lot to do with number theory. So many of you will have been bored by me in previous talks discussing the connection between sums of either random multiplicative functions or deterministic multiplicative functions like Dirichlet characters and multiplicative chaos. So I'm not going to discuss that today. I'm going to talk about a different thing. And that's the connection between multiplicative chaos and statistics of L functions, and more specifically, shifts of the Riemann Zeta function. Okay, so this thing that's in the middle of the slide here, this is going to be basically the problem that we're thinking about today. So I want to understand if I integrate the gammath absolute power of the Riemann Zeta function against test functions g, and I integrate over just a short window, so let's say of length 1, but the position of the window is random. Okay, so we're going to integrate on this window of length 1, centered at the point t, somewhere on the critical line, and t is going to be uniformly random on this scale. and I want to understand the behavior of these integrals. Okay, so g will be a nice test function. Think a continuous function, a step function, even just think g is identically 1. That pretty much captures the key ideas. And then, so for any fixed g, this is some number here. And if t is random, this is a random number, a random variable. And I want to understand the distribution of this random variable. Okay, so that's the problem. So if you think of g here just being fixed identically 1, so I just have the integral of mod zeta to the power gamma, that's a pretty concrete thing. And we want to understand the distribution of that thing. Okay, so what does this have to do, excuse me, with the thing I was discussing before? Well, so I already mentioned the Selbig's central limit theorem, which says that log mod zeta at a single random point t on the critical line has a roughly Gaussian distribution. Okay, so if you go back here, so this is mod zeta to the gamma. I can write that as e to the gamma log mod zeta. So log mod zeta is playing the role of x of h in my previous discussion. And log mod zeta has a roughly Gaussian distribution. I said we wanted the x of h to have a roughly Gaussian distribution. Okay, and then maybe I'll go back. So I said we wanted the mean and the variance, so the mean to be 0, say, and the variance to be very close to constant at all points. So in the Selbig CLT, the mean indeed is 0, and the variance is about a half log t at every point. So we have this. And then how about the covariance? Does it decay logarithmically? Well, it does. So there's a connection which was very briefly hinted at yesterday. So in Bonn, it was very good for me. There were 2 talks the day before my talk which gave a lot of details about this. Here it's just been kind of hinted at, but it was mentioned yesterday. There's a connection between branching random walk and divisor statistics, for example, in Kevin's work. And there's also a connection between branching random walk and the correlations of log of the zeta function. This is the same thing that was kind of mentioned in the previous talk. You can just think here, so what's the significance of log correlations? Why is that the thing that comes up? Why do we care about it at all? Well, zeta, you can think, even on the critical line, is kind of roughly like an Euler product. This is related to what Will was discussing yesterday. So log mod zeta is roughly like a sum over primes. And what happens is that in this sum, you have primes of different sizes. And for the small primes, so p to the it with p small, p to the it doesn't change very much, even if you change t on quite a big spatial scale. Whereas if p is big, p to the it is rotating much faster. So it changes on a much smaller scale of t. So you have this kind of multi-scale structure in log mod zeta corresponding to the different scales of primes. And multi-scale structure is exactly what corresponds to log correlations. Okay, so that's the point here. The thing that gives you multiplicative chaos, that gives you the interesting behavior, is multi-scale structure, and that's what you have here because of the different sizes of primes in the sum. Okay, so if you believe everything I said there, then you might think that this object is quite analogous to the integral g e to the gamma x of h, multiplicative chaos thing that I was discussing before. Okay, it's going to turn out that it is. Right, so maybe any questions up to this point? It could be, but it won't be. Other questions? Yes? So centering, you mean like normalizing term? We'll come to that. Other questions? Okay, so in a minute, I'll talk a bit more about multiplicative chaos and the properties that it has. Before that, I want to say some number theory things. So this is what we want to prove, okay? So I guess this comes to the question that was just asked. So we want to find some normalizing factor that will depend on t, the scale of everything, and also on this parameter gamma, so that if we rescale these integrals, these random integrals by this normalizing factor, this converges in distribution to some interesting limit. Okay, and interesting means 2 things. Firstly, we're going to talk about the conjecture of Saksman and Webb later on. They have a specific conjecture about what the limit should be. And the limit is a limit that's sort of known in some sense on the probabilistic side, so therefore it's interesting. So that's one meaning of being interesting. But there's a more basic meaning, which is that if I took n here to be very large, I could make this just converge to 0 for sort of trivial reasons. And I don't want that. Okay, so I want to find a normalizing factor n so this converges to some non-degenerate limit, some non-zero limit. So the question is there some n for which that happens? And what is it? And what is the limit? Okay, so that's the goal. And again, if you like, just think that g is identically 1. Okay, that doesn't really lose anything. So this, I hope, is a fairly natural kind of question. Can we rescale these integrals in some way so they converge to something non-zero? Okay, now, so I mentioned the Selberg central limit theorem. So maybe it would be helpful to compare a little bit what's going on here with what happens in the Selberg central limit theorem. So the Selberg central limit theorem, I guess, is about 80 years old as a theorem. The initial proofs were somewhat complicated because you had to work around the zeros of the zeta function in a quite non-trivial way. And then about 10 years ago, Radziwill and Sound gave a very nice conceptual proof. So it's now, let me say, not super hard to prove the Selberg central limit theorem. So how does that compare with the situation here? So in this integral, so we usually think of the zeta function kind of renewing itself or starting to renew itself, let's say, on a scale like 1 over log t, because that's the scale of the average zero spacing. So in this integral, which has length 1, we can think that we have maybe about order log t different values or possibly different values of the zeta function. Okay, so Selberg CLT, one random point. Here we have about log t different points. So this is maybe some very, very high dimensional analog of the Selberg central limit theorem. And that's usually a problem. So proving limit theorems, Gaussian approximations, for example, in very high dimensions is usually not so easy to do. Now, another thing is that in the Selberg central limit theorem, what you do is you take this, you don't have to subtract anything because the mean is 0, but you rescale by square root of half log t, and that converges in distribution to a Gaussian. So what that means is that if you do anything in the proof which approximates log mod zeta, which you do in the proof, as long as the error that you make is smaller than square root log t, it disappears in the limit. Okay, so if I do any manipulations with this to make it easier to work with, which I do, for example, I move off the critical line usually a little bit, as long as the error that I make is small compared with square root log t, it will just disappear. But here it's very different. So here, where does log mod zeta appear? So it appears in the exponent. Okay, so this is e to the gamma log mod zeta. So even an error of size big O1 is no good for me. If I'm making error of size big O1 in the exponent, that corresponds to a multiplicative factor here, and I'm trying to prove convergence in distribution, so I can't do that. Okay, so what I'm trying to convince you of here is that maybe this is a rather more challenging problem than the Selberg CLT. Okay, we have lots and lots of values of zeta at the same time, and we need to understand their values much more precisely than we do in the Selberg CLT. Now, so fortunately, because of the way that all these values of zeta come together in this integral, understanding it is not actually as hard as either of these things. Okay, because we couldn't do either of these things. So we couldn't prove a multidimensional limit theorem for zeta in this many dimensions, nor could we do this. If we could do this, this would pretty much solve the density conjecture of Ramachandra. So there's a famous conjecture that the values of zeta on the critical line should be dense in the complex plane. And if you could do this, that would sort of more or less resolve that conjecture. So we can't do that. So fortunately, the problem isn't actually as hard quite as either of these things. But I think it's fair to say that it's rather more challenging than proving the Selberg CLT. Okay, so that's something you can think about. Another thing you can think about is what should this normalizing factor n be? can we get some idea of it? So what's the role of n? Maybe if I go back. Okay, so we want n to be such that this thing, when we scaled by n, converges to some non-degenerate limit. So n should capture the kind of typical size of these integrals. Okay, so we want n to be such that for most t, this is kind of on the scale of n. So how can we figure out what n is? Well, an obvious thing is just to average over t and see what happens. Okay, so if we do that, so if I average this thing over t, I can obviously swap the integrals. So the integral over t comes in here. And this now should be very familiar to the kind of hardcore analytic number theorists in the audience. So this is just like the gammath moment of the zeta function. Okay, this shift by h doesn't make any difference to anything. So we expect, or we know, in order of magnitude, and maybe assuming the Riemann hypothesis, how these moments grow. So this should grow like log t to the power gamma squared over 4. So an obvious guess for what the normalizing factor n should be is it should be log t to the power gamma squared over 4. And you can think about, is that actually the correct choice? Okay, and what you can see just from this calculation is that we certainly shouldn't take n any bigger than that. Okay, because if I rescale by something which grows faster than log t to the gamma squared over 4, so I divide here by n, where n grows faster than log t to the gamma squared over 4, this will just be going to 0. And therefore, in L1, in probability, everything will be collapsing to 0. And I said that I don't want that. So I want to choose n so I get a non-degenerate limit. Okay, so n shouldn't be bigger than this, but n might be smaller than this. Okay, it might be that the reason this average has this size is because there are some rare values of t which kind of inflate the size. And actually for most t, which is what matters for the limit distribution, the scale is smaller. Okay, so you can think about that, and we'll come back to that. Okay, maybe any questions up to here? Okay, so let me now go back and talk a little bit about chaos on the probabilistic side. So there was this parameter gamma in the construction, okay, and I showed you that the expected weight that you give to the point h, which is just the moment generating function of x, behaves like this. So you can see that as gamma increases, the expected mass is going up. And if you look inside this expectation calculation at the kind of scale of x which is contributing here, the size of x that contributes also goes up with gamma. Okay, so as gamma increases, this expectation goes up, and the values of x which make the main contribution to the expectation also go up. And for the number theorists, this again should be very familiar. So we know that if you look at the 2kth moment of zeta, that's dominated by values where log mod zeta is like k log log t. Okay, so as k increases, you go more and more into the tails of a distribution. So as gamma goes up, you're kind of focusing more and more on the tails of a distribution of the random variables x of h. And then in the integral here, so there are infinitely many points, okay, a priori, but points h and h prime which are very close together, the behavior of x of h is really the same. So I showed you in the zeta case, if I go back, so there are really only finitely many values, like order log t, different values here, or possibly different values. And the same happens in general. So this is a priori infinite integral, but really there'll be finitely many values that count here. And so what will happen is, when gamma gets big enough, you'll be so far into the tails of the distribution up here that you'll probably never see any such size of x of h on your integral. Okay, so in the expectation here, you see the whole distribution of x of h. You can go as far into the tails as you want. But in this integral, really, you only have finitely many values. So if you're too far into the tails, probably you won't see any of those values. Okay, and there's a transition in gamma which happens. So when gamma is small, that isn't the case. You probably will see the size of x of h, which contributes here inside your integral. When gamma is too big, you probably won't. And the critical value is exactly where this change happens. Okay, and the value of gamma c as a number, well, that depends upon the variance of the x of h's, the dimension of the space you're integrating over, various things. So I'll tell you in a second what it is in the zeta function case. But conceptually, this is what the critical value is. So it's the value where this change occurs. Okay, and what we know, so Kahan in the 80s, at least in some special models, understood that as long as you're below the critical threshold, the critical parameter, if you rescale these integrals by the obvious thing, okay, by the expectation, so this would be analogous to rescaling by, if I go back, so analogous to rescaling by this. So if you're in the if you're in the subcritical case, if you rescale by that, you get an interesting limit, a non-degenerate limit. And what's being understood only much more recently, I guess in the last 15 years, maybe, is that in the critical case, something different happens. So in the critical case, you should rescale not just by the thing in the numerator, but by something a bit smaller. So by the thing in the numerator divided by this standard deviation type factor. And then you get a non-degenerate limit. Okay, so this is the key thing that you need to kind of take away about chaos. So in the subcritical range, rescale by the obvious thing, just the expected size, and everything will be okay. The critical parameter, don't do that. If you do that, everything will just collapse to 0. So rescale by this slightly smaller thing to get an interesting limit. So if you don't get that, well, we've only understood that for 15 years. So we've understood the Gaussian distribution for 200 years at least, so it's not so bad. But this is what I'm claiming is the case. Yeah, so for larger values of gamma, the distribution is just kind of concentrated on the very highest values of x of h. In the critical case, if you rescale by this, you get a non-atomic distribution still. Right, so in the zeta example, I claim, so first of all, the standard deviation is like square root log log t. That's the same square root log log t in the Selberg central limit theorem. Okay, it turns out that the critical value is 2. Okay, so you can calculate, and that's what it is. And then that leads to an interesting kind of state of affairs, because on the one hand, the critical chaos is rather harder to work with than the subcritical chaos. So we usually think that doing things in the subcritical case is what we should do first, because that's easier. But on the other hand, on the zeta function side, 2 is a very nice exponent. Right, so if I go back, so if there's a 2 here, then we're very excited, right? We can expand the square. That's great. If it's some fractional exponent, it's very unclear what to do. So it's sort of balancing act. So if we're in the subcritical case, it would be easier on the probabilistic side, but for the number theory stuff, 2 is very good. And also, if you can do the critical case, I mean, that's interesting, because you have these non-trivial renormalizations that you have to do, and you get results that you might not expect. So for example, in the character sum problems, which I'm not talking about today, but some of you will have heard me talk about, you get more cancellation than you expect, precisely because there's a connection with the critical chaos. You get this extra scaling factor. Okay. So now we come to the third point I promised in the talk, which is the conjecture of Arrow and Christian from about 10 years ago. So this is an approximate statement of their conjecture. The actual statement is a bit more kind of highfalutin than what I wrote here. But I think this captures the key points of what they want to say, and also is hopefully understandable given the things I said up to now. So for all parameters gamma up to and including the critical one, okay, so I told you that 2 is the critical exponent, so everything up to and including 2. And any nice test function, let's say step function g of h, they conjecture that if you take these integrals and you rescale by n, So t here is the random thing. Okay, t, as always, is uniformly random on the critical line. So this should converge in distribution where n, the scaling factor, is what? So if gamma is subcritical, n is what we guessed before, is log t to the gamma squared over 4. And if gamma is critical, so gamma is 2, if you plug gamma equals 2 in here, you just get log t. Okay, that's the log t from the second moment of a zeta function. But you should rescale not by log t, but by log t divided by root log t. Okay, this is the same as, this is this extra factor here. So they conjecture that if you rescale in this way, you'll get an interesting limit. And they also conjecture what it is. So it's so you should remove probably this part here. So well understood, I think, is that's an exaggeration. But some kind of perturbation of a multiplicative chaos measure which comes up in the probabilistic theory, and about which we know some things. So for example, we understand the tails of the distribution. Okay, so again, this is the conjecture. So for any nice test function g, just think g is identically 1, if you like. If we rescale in this way, this should be converging to some limit, which we understand somewhat, and in particular is a non-degenerate. Okay, and so the result I want to explain a bit for the rest of the talk is this result of myself and Saksman and Webb. So we can prove their conjecture in the critical case where gamma is 2. And this is the first and only so far known case of a conjecture. And so in particular, if you take g to be 1, the claim is that this integral, rescaled by the non-standard rescaling, because we're in the critical case, this should converge in distribution to some specific thing, but don't worry about that, but should converge to some non-degenerate limit as t tends to infinity. Okay, so in the rest of the talk, I want to say something about the proof of this theorem. But before I do that, are there any questions about what I said up to here? Yes?
Did you do the imaginary part of log theta?
I doubt it. I don't know, but I doubt it. Yeah, so you could, conjecturally, you could certainly understand that. In terms of proving anything for zeta, I think doing anything except for the exponent 2 is going to be very difficult. Yes? 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 Maybe you would. So I think I'll show you some steps in the proof later. I think lots of things would still go through, probably. Yeah. I don't swear to it, but I think it would probably be okay. Is there another question as well? Yes?
Yeah, so in the limit, can you separate somehow the contribution of the small primes?
So you could do things, for example, so if you took a smaller range of integration here, this is kind of related to the question that you were asking at the end of the previous talk, you'd see a part factor out which corresponded to the small primes. And what was left would it would concentrate around something, and that would be the large primes piece. So if you took a range of integration here which was smaller than this, on that piece, the contribution from the smallest primes would basically be constant, depending on t, and you could factor that out. So you could do something like that. So I'll show you, I guess it won't be clear from what's written on the slides, but everything is very quantitative in most steps of the argument. So it doesn't have to be an interval of length 1 here. There's some, you could make this a bit smaller. Other questions? This is unconditional, yes. As I'll also explain in a minute, even assuming mega conjectures probably won't help. So we'll see in a second. But this is an unconditional result in particular. Other questions? Yes. Yeah. Okay. So let me talk first in kind of quite high-level terms about the proof of this, and then if you're a number theorist and you're upset that I haven't said much number theory stuff so far, I will finish the talk with some basically purely number theoretic things, so you can be happy again. Okay, so how could you try to prove something like this? Well, we want to prove convergence in distribution. A general thing, which usually I actually hate, but in this case it's probably a good idea, is you could try and use the method of moments. Okay, so what does that mean? So you have some sequence of random variables, you have some target, which they're maybe converging to, and the target has to be nice enough, and I'll say something about that in a second. So if you can show that every moment of your sequence of random variables converges to the corresponding moment of a target, okay, and you don't need any uniformity here, but you do need this for every fixed moment. So if you can do that, then you can conclude that your random variables indeed converge in distribution to the limit x. And nice enough basically means that these moments shouldn't grow too quickly as a function of r. Okay, so typically the moments increase as r goes up, but you don't want them to increase too fast. And if they don't, this is a very general machinery, and you can get convergence in distribution. And in particular, for example, the Gaussian distribution is nice enough. So if you have a sequence of random variables whose moments converge to the Gaussian moments, you get convergence in distribution to the Gaussian. And this is how the Selbig central limit theorem usually is proved. So you take log mod zeta, you show that for most t, this is approximated by something whose moments you can compute, some kind of Dirichlet polynomial over primes, usually. And then you compute the moments, and you show they converge to the Gaussian moments. Okay, so we could try to do this in our problem, so let's see what might happen. So there are quite serious difficulties. So one, which the people who know about chaos will already have spotted, is that the limit distribution here, so if G is 1, this is just the total mass of the chaos. So the limit distribution is not nice enough. Okay, its moments, in fact, don't even exist past the first moment. So that's a fairly serious problem. Yes, it has polynomial tails, in fact. So the fractional moments below the first moment do exist, but that doesn't help for the moment computation. And the other thing, and this kind of relates to Dimitrius's question, is supposing we could overcome this first thing, so we were trying to compute all the moments. Well, to compute the rth moment of this, that's something like the 2rth moment of the Riemann Zeta function. And we need asymptotics. Okay, we're trying to prove convergence, not just order of magnitude. And even assuming, for example, the Riemann hypothesis, we can't do this. Okay. In fact, we can't even do the 6th moment, even assuming the Riemann hypothesis. So this is a very serious problem. And Brian, who was in Bonn when I gave this talk before, asked if you assume the conjectures about the asymptotics for moments of zeta, would that help you? And I think even that probably would not help. So in theory, if you plug in the conjectured asymptotics, I suppose you must get the right answer for these high moments. But the thing is that to deal with point 1, you need to compute not actually the moments of this, but the moments of this thing adjusted in quite a complicated way. And I think doing the computation, even assuming the conjectures, would be very, very difficult. So as I'll show you, we get around this in a different way. But I think even assuming the kind of mega conjectures would not help, probably. Yes. Yeah, so if I want to compute the rth moment of this, so it's a kind of 2rth moment where you have lots of shifted copies of zeta. Okay, so if you assume the conjectures, you have some formula for what that is. But what you really need is not, and the formula would be rather complicated, I think. But what you really need, because you need to do something to correct this point 1 here. So what you're really going to need is not this, you're going to need that with some other kind of twisting factors in these integrals. And I think plugging in the conjectures for the moments of zeta with these twist factors and computing everything, getting an answer, is going to be extremely challenging, even assuming the conjectures. So it's, I suppose, in some sense, a doable computation. It must be, I suppose, but I think actually doing it would be not doable, probably. I guess when this is all written up, somebody can see and prove me wrong. Okay, other questions? Okay, so what I want to talk about for the rest of the time is the kind of plan of our proof and how we get around these two issues. And I'll give, first of all, quite a kind of high-level discussion, and then I'll talk in as much time as I have left in a bit more detail about two of the points. Okay, so the proof splits, very loosely speaking, to a kind of number theory bit, which is the part I'm going to focus on here, and also a probabilistic part, but I'll say something about that as well. Okay, so we start off with these integrals with zeta inside them. And the first thing we want to do is to replace zeta by a Dirichlet polynomial. Because Dirichlet polynomials are the kind of things we can work with and maybe show match up with the random side. Zeta itself is harder. So the first step is to show for most t, okay, only interesting things that happen for most t, because I'm trying to get a distributional result. So I want to show for most t, we can replace zeta here up to some kind of scaling by a Dirichlet polynomial, which is a nice Dirichlet polynomial. I'll explain what that means later. And in particular, has length a bit smaller than root t. And this, if you're a number theorist, you might find a bit surprising. Yes, yes. So we usually think that you can't approximate zeta by a Dirichlet polynomial of length less than root t. But here, exactly as Henrik says, making use of this integral, although it's only a very short integration, you can. So I'll show you. And then, what might be even more surprising is that you can replace this Dirichlet polynomial, d of length about root t, by a really short Dirichlet polynomial. So a Dirichlet polynomial of length t to the epsilon, or even smaller than that. And not only a really short Dirichlet polynomial, although that's important, but a Dirichlet polynomial which is supported only on smooth numbers, so numbers with small prime factors. This is important because a Dirichlet polynomial supported on smooth numbers is kind of quite like a product. And products, Euler products, they're the kind of things we know how to work with on the random side. Okay, and if we can do this, which we can, this gives us hope of being able to overcome this issue 2 here. Okay, because the reason that we can't compute high moments of zeta, in fact can't compute anything past the 4th moment, is because zeta usually we think of as being like a Dirichlet polynomial of length root t. We can only really work with Dirichlet polynomials of length up to t. So the 4th moment is like root t squared squared. So that's t squared, that's okay. T we can just about handle. But the 6th moment would be like root t cubed squared, t to the 3 over 2 squared, and that's no good. T to the 3 over 2 is too big. Okay, but if we have Dirichlet polynomials of length t to the epsilon, we can compute arbitrarily high powers of this and still be below this t threshold, yes? It can be actually reduced to that. And also it's doable once it's been reduced. Yeah, sure. Yeah. So my claim is that we can reduce to this length. I'll show you. And after that, you can then make the rest of the argument work. Yeah, so if we can do this, which we can, then we'll be able to overcome, maybe, the issue in the second part of computing very high moments. Yes?
In this step, if we're assuming like splitting conjecture or something, that means we can, maybe we only care about primes small enough, so that
I suppose so, but in the splitting conjecture, you would have the zeros part as well, which you would have to deal with. So the kind of point here is I never want to work with the zeros because they're scary things. I just want to work with Dirichlet polynomials. Okay, any other questions about this? All Great. So let me. So I'll say something in more detail about these 2 points to finish the talk. But let me also say kind of the end of the proof, the more probabilistic bit. Yes. Which bit? No. So the source of a log is here. So what you have to do is work not with these integrals, this is also related to what John asked, but with these integrals with some kind of barrier inside. Okay, so barriers we heard a tiny bit about in the previous talk. So barrier is just some Dirichlet polynomial, in fact, that restricts the size, restricts the growth of this Dirichlet polynomial P and also of its kind of sub-Dirichlet polynomials. So you have to insert this for the next step to work, and also, in fact, for the proof of 2 to work. So I'm lying a bit the way I've written this. And when you insert this, you can insert this because for most points in the integral, this barrier is satisfied. But when you insert this and you compute the averages of everything, this is where the log-log factor comes from. So this barrier that you put in with probability 1, if you like, for most points it holds, so you can insert it. But when you compute averages, this reduces the size of the averages a bit. Okay, and then 4, so after this barrier is inside, we can compute time moments of this. They match the natural random model, the thing that was kind of mentioned in Will's talk yesterday, where the p to the minus ITs are just replaced by these Steinhaus random variables, uniform on the unit circle. And not only do they match the random model, but because this barrier is here, they don't grow too fast. They grow quite fast. They still blow up when you take higher and higher moments, but not too quickly. And this kind of overcomes the limitations of the method of moments that I mentioned at the start. So what you can do now is you can show that the moments here aren't growing too quickly, and they match the random model. So now you can invoke something like the method of moments and say that actually the distribution here is like the distribution in the random model. And if you can do that, then you're happy because in the random model, Error and Christian already proved that you get convergence to the chaos measure. So in the paper where they conjecture what happens for zeta, they prove in a random Euler product model for zeta that you get convergence to the chaos. So after you can pass to the random case, which is after all these previous steps, you can invoke this result. Yes, the random case is for all gamma, but we can only do the previous steps when gamma is 2. Or all gamma up to including 2. Yeah. Yes. So I think, I mean, error is here, but I think they only do gamma less than or equal to 2 in the paper. Yes. Almost all of them. Yeah, this fails, everything fails, unfortunately. Okay, so I guess if you could get to this point with a short Dirichlet polynomial, you could do this, yes. It's the beginning, yes. Yes, it's the number theory part, yes. Okay, anything else? Okay, so I have 10 minutes, so hopefully that's enough to say something about points 1 and 2. So, okay, we want to approximate zeta by some Dirichlet polynomial. Okay, the only clear thing to do is what you always do, which is invoke the approximate functional equation. Okay, so zeta is the sum of 2 Dirichlet polynomials of length about square root t. One of them twisted by this chi factor, so this is a rapidly oscillating term from the functional equation for zeta. And there's also a very small error here which makes no difference to anything, so I'm ignoring that. And if you expand out the square, so this you can do for squares but not for anything else, what happens is that, so chi has absolute value 1 on the critical line. So the mod squared of this part and the mod squared of this part are the same. So you just get 2 copies of this thing. And then you get another term, a cross term, which involves chi, this rapidly oscillating piece, and also the square of, let's say, this one. And as Henrik said, because you have an integral here, albeit quite a short integral, of some oscillating thing, you get more cancellation here. I'll explain on the next slide how you can actually prove that, but you do. So we want to show that the contribution from these cross terms is small, And small, and this is another important point here, so small just means small compared with the rescaling that we're doing. Okay, so we're allowed to make fairly big errors here because we're rescaling everything by log t over root log t. So if we make a mistake which is smaller than this, that's okay. That's another important feature of the problem. And then I said we could have here not a Dirichlet polynomial of length root t, which we currently have, but one which is shorter and also nicer in some sense. So I'll explain that as well. So we can replace this by something a bit different, again making an error for most t, which is smaller than log t over root log t. Okay, so how do you do these things? Well, to get rid of the cross terms piece, just move the line of integration to the left in the complex plane. So this is something that people do when they prove the fourth moment of zeta, for example. So in the cross term, you have chi, which is holomorphic. You have just the square of one of these pieces, not the mod squared, just the square. So everything is holomorphic, so you can move to the left. And if you compute the mean square on the 1/4 line, what happens is you get some kind of polynomial blow up from this sum moved to the 1/4 line, but this is exactly cancelled by the size of chi. And you don't get any log blow up, which comes from being on the 1/2 line. So you actually win something, you win much better than this actually. Okay, and as has already been mentioned, it's important here that we have an integral. Okay, this wouldn't work at a single point. Right, now what do I mean by nice Dirichlet polynomial? So I said that we want at the end to get a Dirichlet polynomial supported just on smooth numbers with small prime factors, because that's close to an Euler product, which is the kind of thing we can work with. So I want to set things up for myself to make it easy to get there at the next step. So what I want to do is to replace this Dirichlet polynomial by something which is a product. So a product of something over smooth numbers and something over rough numbers. Rough numbers means all their prime factors are bigger than capital P. Okay, so all the prime factors here are at most P, all the prime factors here are at least P. And the other thing to note here is that this Dirichlet polynomial doesn't go up to root t, it goes up to something a bit smaller than root t. Okay, and why are we allowed to do this? Why can we replace the thing at the top by the product of P and R? Well, if you use just the mean value theorem for Dirichlet polynomials, it will tell you that the difference between having the Dirichlet polynomial at the top and having the product of these things is like the sum of 1 over n over all the numbers which occur in here but don't occur in this product of P and R. And what are those numbers? Well, they're the ones where the p-smooth part is bigger than x, but usually the p-smooth part of a number isn't much bigger than p. So if you choose x appropriately large compared with p, there won't be many such things. And also, because I've trimmed off the length of this rough Dirichlet polynomial, the sum of 1 over n over all the things between t to the half minus log o1 and root t. But if my log o1 should be small, that will be less than log t over root log t. Never exceeds square root t. Okay, so I can remove the largest terms here at the cost on average of something which is less than this. And I can keep this Dirichlet polynomial very short. This is just an anatomy of integers type thing. We're using the fact that most numbers have p-smooth part not very much bigger than p. And most numbers, when weighted by 1 over n, which is what happens for the mean square, aren't super close to root t. Okay, and if you choose everything properly, so p is going to be t to the log o1, x is bigger than p, but still t to the log o1, you can make this smaller than the t to the log o1 here. Thank you.
P is smooth, right? Smooth numbers.
Yes.
The largest prime in P is t to epsilon, right?
Yes.
And this epsilon is smaller than O of 1.
Yes. Yes.
Yeah. Just trying to catch.
Yeah, that's right. So P will be like, maybe I can give some parameters. So P will be like, let's say, t to the 1 over some big power of log t. And x will be like t to the 1 over some smaller power of log, something like that. Okay, and the total length of it, so by length, I guess I've been saying that all along. So length just means the largest number from a Dirichlet polynomial. So the length would be like x times t to the half minus little o1. And if x here is small compared with the t little o1 here, this whole length is still less than root t. Okay, so maybe I have 5 minutes, so I can do that, I think. So let me talk about the second step. So I want to show that I can replace d, which is the product of p and r, just by p up to some scaling factor. Okay, so yeah, usually the rough Dirichlet polynomial just contributes some kind of constant. And this is something that definitely doesn't happen in most analytic number theory problems. So usually the rough Dirichlet polynomial, the large primes, corresponds to the zeros of zeta. This is the really hard thing to work with. Okay, but what I claim is that here, this is just going to go away. Okay, and why is that? Well, here's the heuristic reason. So the rough Dirichlet polynomial only depends on the primes bigger than capital P. Okay, so it involves terms like this, where little p is bigger than capital P. And these are very rapidly oscillating. So if you change t or h just by a little bit, this is going around the unit circle quite fast. And what you should think is that in this integral of length 1, as I vary over this integral of length 1, I go around the unit circle lots and lots of times on these large primes. And so you kind of see lots and lots and lots of copies of everything that's happening, and so you get concentration of this large primes piece. Okay, and this is an idea that for the chaos people is maybe quite familiar. So how can you prove this? Well, you can try and compute something like a variance. Okay, so I claim that for most t, this integral of d is the product of the smooth and the rough Dirichlet polynomials, is very close to the integral of the smooth part with this scaling factor. So you could try and compute a variance. I think there's a square just visible at the end here. And the kind of scale of everything inside should be like log t over root log t. And I'm squaring, so the scale of everything should be like log t over root log t all squared. So I want some saving compared with this. And then I'll be happy. And this we can certainly compute, because this is something like a fourth moment. Okay, there's a square here, and there's another square up there. And these Dirichlet polynomials have length less than root t. So we can do this. We only get the diagonal contribution. Everything is good. But if you do this, the answer won't be what you want. Okay, the variance will actually be too big because of some diagonal type contributions, essentially. So you need to insert a barrier here. So I haven't really explained what a barrier is, but it's not this integral itself, which is close to that. It's this integral with some suitable barrier inserted, which is close to the corresponding thing, also with a barrier inserted there. And the barrier you can encode with a short Dirichlet polynomial. And because I have this little O1 room here, if I plug in a short Dirichlet polynomial, still everything is less than root t. So still you can compute the fourth moment, and it's only the diagonal terms which count. Okay, so you get this concentration, you can replace the rough Dirichlet polynomial by this piece. And now it's only the smooth Dirichlet polynomial, the short, smooth Dirichlet polynomial that's left, and now you can compute high moments. And that, so you can do it, the answer will agree with the random case, but you need to know how big the moments are, how fast they grow. That's also a rather non-trivial thing. But that I don't want to talk about here. I have 1 minute left, so I'll finish there. Thank you very much.
Questions for Adam?
Yes.
For gamma equal 1,
Yes.
it's not functional. It's where the error term is large.
So when gamma equals 1, it really is still a fractional moment because, let's look here, I guess. So it would be the absolute value of zeta to the power 1. Right, so that's the absolute value of zeta to the power 2 times a half. And a half is still fractional. I mean, the only obvious thing to do is to expand out the square. There's no other clear way to proceed here. It's the same reason, for example, that we don't have an asymptotic for the first absolute moment of zeta. We know its order of magnitude, but asymptotics we can't do.
The same one, what about the fourth moment?
Yeah, so The fourth moment, maybe you could do some of these steps, but I think when you get to here, you would have a problem because the fourth moment now you're squaring, so you have something like an eighth moment, and this again we can't do. Well, you need to know that this concentrates around that.
You can always folder out to the second moment.
Let's see. So I need to, maybe on a kind of more conceptual level. So for the second moment, if you just guess the size of a second moment as being like the mean square, you get the correct answer. For the first moment, if you just guess the size of the first moment, you don't get the correct answer. There's a random matrix theory correction in the constant. So that needs to appear somewhere. It's not clear where this is going to come from. So anything where you need some information about the zeros looks very hard to do.
A family of L functions where the eighth moment is known. Could you
So this, I suppose, you could do, yes.
Oh, my other question is, why do you hate the method of moments?
I think that, okay, we should talk about it over lunch, I guess. So usually when you apply it, you just start computing. And I don't like that. In lots of problems, there's more structure that you should be able to use. But here, the method of moments is the only thing that we seem to be able to use.
I guess we can save further discussion for lunch. Let's take another 10 minutes.